Hello, everyone. My presentation is about, thank you. My presentation is about hacking Windows RPC and RasMan. Sorry, 1 second. Okay. So as an overview of what I'm going to go through today, I'm going to go over a high-level overview of the exploit first. Then I'm going to do a crash course on Windows RPC. Then I'm going to talk about how I went about trying to exploit the RasMan service and then trying to get privilege escalation on it. So a brief introduction slide. I work at Trail of Bits, like he was saying. This is my first time at Summercon, and I like to do computer stuff in my free time. So I did this research when I went abroad in South Korea during my last semester of school. So, yeah. For context, this is a pretty simple exploit chain, but for context, I'm someone who's never used Windows before this in my life. I didn't even know how to take a screenshot on Windows. And I've used Linux my whole life, and not my whole life, but for the past several years. So I had no idea what I was doing, but I wanted to be more well-rounded as a security researcher. So the goal was just learn Windows exploitation and then write an end-day Windows exploit for a logic bug. I didn't want to start with memory corruption. So first, I randomly picked a CVE. I picked CVE-2025-59230 first. And then after getting into the process, I realized that I had to chain it with the other CVE that came out a couple months later, but it was known at the same time as the first one. So the whole idea behind this exploit is that you have this service that's running called RasMan in Windows, and it's going to be running under system privileges. And assuming that you have an unprivileged guest account, the goal is to get a local privilege escalation. So the first step is that you're going to crash the RasMan service that's currently running in Windows. And you're able to do this as an unprivileged user. So that is the CVE-2026. That's the bug that corresponds with that CVE. And then after you do that, you can impersonate the RasMan service, and you're still running as guest. But once you're able to impersonate it, you want to trick a privileged client into connecting to it, and that privileged client should also be running as system. And then that client thinks it's the actual RasMan server and that it's actually running a system, but it doesn't do appropriate checks, so it connects to it anyway, and that's CVE-2025-59230. And then after that, you can make a series of calls and get privilege escalation, ideally. So also, how many of you guys have some sort of familiarity with Windows and Windows exploitation? Okay, cool. So what is RasMan? RasMan stands for Remote Access Connection Manager, and basically, all you need to know about it for the context of this talk is that it's an RPC service that lets your Windows create remote network connections. Beyond that, the important thing is that it's an RPC server. So everything that we learn about exploiting it can be applied to other RPC servers and clients as well. So I use this really nice application called RPC View. And RPC View lets you get more information about RPC servers. So if we wanted to learn more about the RasMan RPC server, we can start by looking for its process ID in RPC View, and then we'll notice that it's the process ID 6880. It's running an svchost.exe, so we know that. And then we see that in that process, there is about 4 RPC interfaces registered, but the one we're looking for is Remote Access Connection Manager. And you'll see that it says that it has 16 functions registered to it. It has a UUID. This will all make sense later on. Then we can also see that it has 2 endpoints registered to it. So these are 2 ways that you can communicate with the RasMan server. And then finally, it has an interface, which I'm going to explain later down. But it's basically all the functions that the RasMan server makes available for clients to call. So now I have to do like a mini crash course on how RPC works for all of this to make sense. And it's going to be pretty boring, so I'm sorry ahead of time. But RPC stands for Remote Procedure Call in Windows. And it's a form of inter-process communication where 2 processes, whether they be on different computers or on the same computer, can communicate, and the client can call functions that the server implements the logic for. So the client will call the function, the server will invoke the function, and then return the results of that function back to the client. And Windows has this thing called the RPC runtime library, which when you write an RPC client or an RPC server, you use the RPC runtime library, and that library is going to do all the hard work of, let's say, like when you call a function from an RPC server, the runtime library will take care of marshaling the arguments and then actually reaching out to the server, and then when it gets the return results back, like marshaling them back. So this way, in the client code, you can literally just call a function from an RPC server like you would call a regular function in that client's code. So this is the RPC interface that I was showing in the screenshot earlier. So the interface will define all of the functions that the server is going to make available for the client to call. And you'll notice, this is cut off, but you'll notice like it has the function and then the types for the arguments and the return value. And then you'll also notice the interface has a UUID, which is used to identify it, and the version of the RPC that it's using. So in order for the clients to know how to reach out to the RPC server, RPC servers are assigned a string binding, which is kind of like an address for the RPC server. And it's made up of 3 parts, the protocol sequence, the network address, and the endpoint. So protocol sequence is just going to be either TCP, UDP, or local remote procedure call LRPC. And then the network address is going to be, this can vary, but it can be like the IP address or the name of the machine. It depends on what protocol you use. And then if you're using like a local protocol, or if you're using local remote procedure call, the network address is going to be empty. And then the endpoint is also going to be protocol dependent, where depending on what protocol you choose, you can assign like a port name or a port or a ALPC port name or a named pipe name. So that's how it's used to identify the actual endpoint that's associated with the server. So this is just an example of what a string binding would look like. So there's 2 types of endpoints in RPC. There's well-known endpoints, and then there's dynamic endpoints. Well-known endpoints are known ahead of time, so the client can just hard code the actual string in its code. But dynamic endpoints are not known by the client ahead of time. And you would use dynamic endpoints in a situation like if you're using a TCP port, and if you want your RPC server to run across many computers, you don't know what ports that computer is going to have free. So you can use dynamic endpoints, and then Windows will assign you a free port based on like whatever's free on that computer, and then that would be your dynamic endpoint. So in order to find out how to reach your RPC server, the client has to know the value of the dynamic endpoint. So that's why there's this thing called the endpoint mapper. So when your RPC server starts up, it can tell the endpoint mapper, which you can think of like a database, that this UUID corresponding to this interface is associated with this port, and then the endpoint mapper will go like, okay, it'll store that information, and then the RPC client can ask, based on that UUID, what's the associated endpoint, and then the EPM will reply back and tell it the value. So in addition, so when RPC clients and RPC servers like sync up, there's a struct representing all of the information that's associated with their connection, and that's called the binding handle. And you'll notice it has values like the protocol sequence and the endpoint, which we just discussed, but it also has some new values. And this is simplified. A lot of what I'm explaining about RPC is like very, very simplified. So this is not like completely, like this is not everything that's in the binding handle. This is a small like picture of it. But in order to make sure that the communication between the client and the server is secure the way you want it, Windows exposes some ways for you to like specify, I want this authentication level, this authentication service, et cetera, which I'm going to talk about later. But when I like first tried to learn about RPC security, it was very confusing because there's so many like edge cases and different different configurations that you can have. It felt like this, and I was having a hard time really narrowing down like what to mention in this talk. So I made this like very, very, very simplified diagram that that just touches on like stuff that's relevant to understand what I'm going to talk about later. Basically, as a TLDR, the RPC client can set these values in the binding handle, and the RPC server can deny or allow access based on some checks that it has, and the client can do the same thing. So in RPC, you don't have security by default, as in you could not have any of those things enabled, and the client would still be able to connect to the server. So you have to kind of go out of your way to like provide or to like add these security checks. So by default, if you're using authentication protocol in RPC that has like transport authentication built into it, like named pipes or HTTP, all Windows is going to do is make sure that you provided some valid authentication credentials when you're trying to connect to the RPC server. But beyond that, it's not going to do more fine-grained security, such as saying, are you allowed to access this specific interface or this specific endpoint? So that's up to the server to configure. So there's like various functions in the RPC runtime library that allow the server and the client to configure these like security checks. So you can specify access control list or a security descriptor for like the various parts of your RPC server, like the endpoint and the interface, saying only this person or like this person should be able to access this part of my RPC server. And you can like set rules on how what they should be able to do with it. So I know that was a lot of information, and it took me like a long time to kind of understand all this. So if you're like keeping up, good job. Okay, so the first part of my exploit chain is to crash the RasMan server, like I mentioned at the very beginning. So when you're starting with Windows exploit development, first thing you're going to want to do is like go on their website and then see the specific build numbers and the versions for the patch that they put out. And then once you get that, you're going to want to download the patched binaries and the vulnerable versions of the same binary from this really helpful website called WinBinDex, which gives you all of these like Windows binaries for like all these different versions. So you can, that way you don't have to spin up a VM every time you want to, get these two binaries of these like two different versions. So after you do that, you can put the vulnerable and the patched binaries in Ghidra, or IDA or whatever, and then you can get this thing called a bin export file and then put it into this really nice tool called bindiff, which will help you narrow down where exactly the patch was in that like giant binary. So I was able to like put the vulnerable and the patched versions of the rasmans.dll, which is the binary that's associated with the rasman server, in bindiff, and then narrow it down that the patch was specifically in this function called getUserData. So I made a very, very simplified version of like what happens in the code at getUserData, and this is the vulnerable version of it. So you'll notice that this code is interacting with a struct called the port struct, and I've reduced it down to 3 fields. There's the status field, and then the port struct also embeds another struct called UserData, which is just a linked list of like UserData structs. And then there's the there's the flink and then the blink values, which is just the pointers to the back and the next UserData structs in that like linked list. So the getUserData code, first make sure that the port status is set to open. That's how it wants it to be. And then after it's set to open, it'll go in and dereference those head.flink and those head.blink values. So if we are able to set the port struct to exactly like these values, where we set the flink to null, so it'll like trigger a null dereference when it tries to do that logic, we can crash the RasMan server, which is the first step of our exploit. So if you think about it, this state that we want to set the port struct in is a contradiction, because if the port is already assumed to be open, i.e. like the status value is set to be 0, the head and the head.blink and the head.blink values should probably be initialized, right? So there's probably another bug and another function in this binary somewhere else. So the steps to narrow this down that I wrote out is first find the path that will set the port struct to this contradictory state, and then see if you can trigger that path as an unprivileged user. And then if you can do that, you can automate it to just do it like a one-off with an RPC client that you write, and then prove that it works. So to do that, to do the first step, this you can do with like static analysis or get like Claude to do it. Looking through like all the functions, there was this one function called portOpenX that handled this port struct before it passed it down to the getUserData. And there's a bug in here because at the very top of the function, it sets the status value to 0, and then it does a bunch of logic in between. But then if some of that logic fails, it'll exit out of that function early, still leaving the status set to 0, but it won't do the cleanup. And the initialization of the head.blink and the head.blink happens at the very end of the function. So we've reached this contradictory state where the status is set to 0, but because we triggered the function to exit early, the flink and the blink values are not initialized. So now that we've done that, we want to make sure that we can reach both the portOpenX and the getUserData functions as an unprivileged user. So 2 things here. First, we have to make sure, are these functions even exposed over RPC, or are they internal functions that are used within the RasMan server, and we have to trigger some other functions to get to those functions. And in addition to that, can we access them unauthenticated as a local caller? So for this one, if we remember the interface that we talked about earlier, the interface should list out all the functions that are available to you, right? So we can get the actual, we can get like the full interface with this very nice tool called NT-Object Manager. There's other ways to do it too, but I used NT-Object Manager, and RPC View also showed you this list as well. But you can see there's like 16 functions that we get, and these are part of the interface. And port OpenX and get user data don't seem to be a part of them, and then none of these like seem to directly call port OpenX or get user data. But if we look a little closer, there's these two functions called RAS RPC submit request, RAS RPC submit request local. So if we reverse engineer that a bit more, we can see that the RAS RPC submit request, and the same for the local one as well, they take in this struct called request buffer. I named these. These aren't the like actual names, but there's like an index within that struct, and there's also payload. And then if you keep going with this, you can see that there's a second dispatch table hidden like further within the binary, and that's reachable through calling this RAS RPC submit request. Honestly, I'm not sure like why it was done like this. I'm guessing it was for like legacy compatibility reasons, but if anyone knows and like wants to tell me after the talk, that would be super cool. So now that we know that, we have to make sure that we can call one of those two functions as an unprivileged user. Oh, okay, sorry, before we do that, so I wrote a binary ninja script to actually get all of the stuff that's in the secondary dispatch table, and it was like 150 additional functions that you could access over RPC or something. And then this is a screenshot of specifically port OpenX, and then you'll see like in the table there's the address to the like actual function stored, and then there's like a validation, the address to a validation function that's called before triggering that function stored. So for each of these like 150 or so functions that are accessible, they seem to have a custom validation function for each of them, where they like make sure that the arguments that you're passing in are the appropriate length and whatnot. So I'm guessing like that might also have some like potential for security research, but I didn't really look down that like hole yet. But there's also an access policy flags. But now we know that we can access all this through RPC, so now we need to see if we can do it via unauthenticated and as a local user. So going back to like that giant, or that access diagram that I had before, so you'll see that the purple is like what this server opts into. So it has authentication, it has an endpoint ACL, and it has a callback. So we have to make sure as a local user we can get through all of those, we can get to the other side. And we can start with authentication. This is like where it registers the authentication, and you'll notice it has the value 9 in RPC server register auth info W, and that 9 translates to specifically the RPC _ if _ autolisten and the RPC if allow secure only flags. So that sounds like it would lock us down, but the thing is, because we are authenticating as a local user, as long as you are like logged in and you're a logged in user, RPC if allow secure only like lets you through. So we can bypass that as a local user. And then next, if we go to the endpoint ACL that it registers, this just means everyone and anonymous, so we can get past that. And then there's this callback security function registers as well. So in RPC, you can register specific security callback functions to do additional like custom filtering. If, for example, you don't want a certain client to access a certain like interface or call a certain function or something like that. So in this case, it seems that as long as the caller is local, it lets you through, and it does like further access checks on a remote-only caller. So we can get past that as well. So now we've confirmed that we can reach this path as an unprivileged user. So now that we got that out of the way, and we kind of have like a mental map of how we would go about triggering this like vulnerable path, we can build it out in an RPC client to make it like very easy to just run as a one-off script. And NT Object Manager, again, makes this very easy. It was like built by James Forshaw, which is a really like cracked Windows researcher, to help him like speed up a lot of his like RPC research. So this, like instead of writing out C code, C++ code, and like building out the client manually, NT Object Manager like automates a lot of the boilerplate for you. So you can just specify exactly what you need, and you can just write a PowerShell script, and you'll have like a RPC client. So the steps that we have to make sure that our client does is like connect locally over that local endpoint, because we want to be like a local user. And then we simply use that RPC submit request function, and then call the port openx, make it error out early, so we get that like vulnerable state in the port struct. And then after we do that, we call get user data, and get user data will see status is set to 0, so we'll get to the null dereference, and then it crashes. And you can verify all of this in WinDebug. So yeah, I was able to get it to that specific state that I wanted. So if you go back and look at the code that, or look at the patch that Windows put out for this, all they did was in the get user data function, they just do a check to make sure it's not null, and then if it's not null, go ahead and do the dereference. However, if you look further, like in the RasMan library, you'll notice that there's like other functions that exist that also like walk down the user data linked list, and they are also, these functions are also triggerable right after like a port openx function call, which does like the vulnerable like error condition without cleanup. So on the current like version of, or on the latest version of Windows, you can still do this crash. However, it's not, you can't do anything else with it because the other CVE that would let you like escalate privileges has been patched. But it was just interesting to see how Microsoft's patches may not, always be correct. So you have to like investigate further. So now that we've done that, we want to impersonate RasMan. So there was some really helpful research done like a couple months ago or a year ago, I believe, by SafeBreach, and the idea was that it was like EPM spoofing. If you guys remember, that was the endpoint mapper. So EPM spoofing is where you register a fake endpoint in the EPM before the real service actually starts, and then you pretend to be the legit RPC server. So as like a visualization, we went over how an RPC server normally registers its endpoint with the EPM, but what SafeBreach was trying to do is that they would have a malicious RPC server that they built, and some of the RPC servers that are like built into Windows have delayed start times when you like reboot the computer. So before those RPC servers could start up and register their endpoints with the EPM, the malicious RPC server would use the exact same UUID as like the RPC servers that it was trying to impersonate, and then register itself with the EPM and be like, I'm actually, this server. And the EPM just goes like, okay, it doesn't do any ownership checks. This is not like patched or anything. This is just how it behaves. So now the EPM has like a vulnerable entry, and what the EPM does is, like, you can have multiple servers try to register for the same like interface with the same UUID, but the one that registers first is the one that's going to be the one that like gets like the function calls from the clients and stuff. So even though the RPC servers that start up late still try to register, it's too late for them. The vulnerable one is already registered. So now that we've won the race, we have to pretend to be the legit RPC server. And we want to make it so that the client gets the client's going to end up talking to us. So we can pretty easily do that because that's just what the functionality of the EPM enables. And that was like the point of the safe breach research, that you could do this and then escalate your privileges, depending on how the RPC server and the RPC client are configured. But his research focused on RPC servers that had a delayed start time. We didn't have that with RasMan, but we could just, we found like a way to crash it. So that was good enough where we could get to this state. So the other CVE, this is like the difference, is that the patched version, you'll notice, adds this SID field to the quality of service, and then this capabilities as well. And previously, the vulnerable version didn't have that. So basically, the patched version checks that whatever it's trying to connect to is running as system, and the old version did not do that. And for some context, there is like 2 RasMan libraries, and when I'm talking about the first vulnerability was in the server one, which is rasmans.dll, and then this vulnerability where it doesn't do the check is in rasman.dll. And then every single RasMan client that exists in Windows uses this rasman.dll library. So that's where the vulnerability is. So now that we know that, we can go back to the access diagram as a reference, and you'll see this is the vulnerable path that it takes, where it doesn't request any sort of mutual authentication, the RPC client. So therefore, a lower privileged RPC server can still connect. So the steps to exploit this are squat the RasMan endpoint, first by crashing it, then registering as it. Crashing it we already did. Then lure a system RPC client into connecting to us. So in order to squat the RasMan endpoint, we have to build out an RPC service that behaves similarly to the RasMan server. And these are the standard functions that you would call to build out a custom RPC server. So first, we want to register that same interface. Otherwise, the EPM is going to reject us. So we want to make sure we have the same UUID, all the same functions that we claim to implement and that are in the interface. And then we want to register at these 2 endpoints, because these are the 2 endpoints that the actual RasMan server exposes. And then we just want to start listening. And you can just build this out. There's a lot of tutorials online on how you can build out your custom RPC server. So once you build that out, that's going to be your evil RasMan's RPC server. And now we're kind of putting the pieces of the puzzle together, where we'll have the evil RasMan RPC server pretending to be the actual RasMan server. And when it receives legitimate requests, it'll just call the RasMan's the legit library underneath the hood. But then we can add on functionality listening to what it does, or modifying some of the requests or some of the responses that we send back. So now we just have to find a target RPC client that's running a system that uses the rasman.dll library under the hood. And then we also want that to be something that we can influence as a lower privileged user. So there's this service in Windows called RasAuto, which is, again, it's not really that important to understand what it does, but basically it just creates a connection to a remote network whenever some program references a DNS or a NetBIOS name or address. And it's very related to what RasMan does. So it uses this rasman.dll under the hood. And as a lower privileged user, you can talk to it. And by writing out certain instructions, you can get it to call specific functions in your evil RasMan's RPC server. So we've achieved step number 2. So all we've done so far is prove that we can get a system or a client running a system, an RPC client running a system to connect to our false RPC server running as a lower privileged user. So there's still the question of how do we use that to privilege escalate? So I tried a lot of things. The first one was trying to do impersonation. I had no ideas how Windows security worked, so it was very confusing. And then I had to read some chapters of this book, which is very good. So as a very, very brief TLDR for people who may not be familiar with how Windows authentication authorization works, you have this thing called the security reference monitor. And then everything in Windows is an object, and it has a security descriptor associated with it, or an access token. So if you're a process and you want to access this file or something, the security reference monitor will take your security descriptor and then check it against that file's access token. So it checks these two objects and then make sure that you have the appropriate access for granting you access to whatever. So in the access token, you have various many things that you can configure. 2 of them I put here because they become relevant later down. But integrity levels, you can just think of a number representing trust. Basically, the higher integrity you have, the higher trust you have, so the more stuff you're allowed to do. And then privileges are just saying that you can do a certain thing in Windows. So SE debug privilege, for example, lets you debug stuff. And then SE impersonate privilege lets you impersonate stuff. So in access tokens, there's you can have 2 specific kinds of access tokens. You can have a lot more, but again, this is very simplified. So there's the primary token and then the impersonation token. And then I was thinking that I could impersonate it, which basically means where I have my process running, and then I temporarily adopt the access token of the client that's connecting to me. So that would have been the system client, and then I act as if I were system. But obviously this isn't going to work because Windows is smarter than that. So there's this thing called the impersonation level, which even if you get an impersonation token, there's an impersonation level associated with it, which says how far you can go when you're trying to act as the thing that you're impersonating. And I kept getting stuck on identification, which meant I could only do read-only actions. So after doing some research, I realized it's because Windows does this checking mechanism when you try to impersonate something, and I was missing many things on that. I didn't have an impersonate privilege because I was a low privileged user. My integrity level wasn't high enough. My user ID wasn't equal to the token user ID that I was trying to impersonate. So basically, this was a no-go. So then I was trying NTLM relay. So TLDR again, NTLM is just an authentication protocol in Windows that you can use where the client goes I want to authenticate to the server, and then the server will send it some random nonce value, and then the client will send the nonce back, sign with the password hash, and the server will check that. So the idea is that you're never sending the actual password hash over the wire. But this can be vulnerable to man-in-the-middle attacks because if you have an attacker sitting in between, you can get that nonce value and then relay it to the server and then pretend to be the victim. But this doesn't work either because in Windows or in RPC, there's this thing called you can specify specific levels, authentication levels, when you create your client, and the RasMan client that I was like talking about earlier uses the highest level of protection, which means everything that it sends over NTLM would be signed and encrypted, so I couldn't relay it and pretend to be it. So I was able to achieve like a very boof privilege escalation, but there's like certain prerequisites that must be true for it, which is probably not going to be configured in like a lot of production environments. This was like purely a logic bug where there's this thing called phone book files that like VPN services use, and in the phone book file, if you meet like a certain set of preconditions, you can specify a DLL to execute, and then that DLL is something you control. So I don't know if this was a success, but yeah, and you can hack RPC2, as in there's like so many different configurations and like settings that RPC clients and servers have, where this was just like the tip of the iceberg. So I'm just going to go into like one specific example here to kind of like show you how it can be like. So if you look at that corner where the client does like the authentication check, if you like zoom in on that, there's like a whole bunch of flags that the RPC server can set. And then you'll notice that there's this like secure only flag that the RPC server can choose to set or not. And the RPC server can also say that it wants credentials, right? However, if like this is the case, and then as a client you provide invalid credentials, you're going to get rejected, and you won't be able to complete the authentication with the server. But if you have this but if you provide no credentials at all and the secure only flag is not set, you're still able to complete authentication. So there's these like weird edge cases where if you have like this thing set and then this thing not set, you might be able to like get somewhere where you're not, like where maybe you shouldn't be. So yeah. So as a recap, like I was saying, RPC servers and clients have like a very complicated authentication model, and a lot of them can like run a system, and they have pretty generous defaults, which can be great for like security research. And I think my methodology like going forward to do RPC vulnerability hunting would be something like where I use static analysis to find what I call a lead. So you can just have a giant PowerShell command that filters through all the binaries on your system or something. And your lead can be an RPC server or client with like some sort of missing or lazy or default or no security configuration, where that on its own may not get you where you want to go, right? But if you're able to find a way to chain it with like further misconfigurations and known techniques, like for example NTLM relay, where maybe I was able to chain it with something where I didn't have like the highest level of authentication set, then that would have been successful. So if you can find a way to chain it, that would be a potential avenue to exploit. In addition, I realized like while I was building out the logic vulnerability, and there was also like some other memory corruption vulnerabilities with like heap overflows and stuff that I found. If you're pretending to be like one of those RPC servers or clients, you're assumed to be trusted by like the other party that you're communicating to. So like for example, with memory corruptions, there was a lot of times where I would be like asked to provide a certain size of something and then like the actual values for it as well. So I could use that trust and like abuse that trust I get by impersonating something and like do a logic vulnerability or a memory corruption. So even though like the initial like lazy or default no security configuration may be boring, it allows you to like do more interesting stuff if you like chain it and you like are very aware and like situation dependent about like how you're going about researching an RPC client or a server. Yeah, that's it. Any questions? Sorry, what was that? Yeah, I can post them on the Sessionize thing. Yeah.
Concerns, qualms, quandaries. Hello.
Hi.
Could you explain again how you were able to impersonate the RasMan RPC server?
Oh, yeah, sure. Basically, it wasn't, hold on. It wasn't that hard just because I crashed the RasMan server, right? And then because there was like nothing registered at that like specific UUID for the that corresponds with RasMan, I could just make a fake one and tell the EPM like, now I'm the RasMan server. And then the EPM doesn't do any sort of checks where it's like, oh, you're not running as like a system privileged account. Why are you trying to register? So just by crashing it, you're able to tell the EPM that you are now the RasMan server.
And then is the UUID just like available?
Yeah. So if you like, for example, this was the screenshot from RPC view. This is like a public tool. And then if you go, like, hold on, if you like go to the decompilation part, you can like get the specific decompiled interface for every single like RPC server that's running on your system, as long as it's registered with the endpoint mapper, because it's like all structs in memory, so you can like reconstruct it, and then you can get the UUID as well. So those are all known and like public. You can find them.
And that's known like at like build time. It's not running on the system. You just have it, the binary. It's right there.
Yeah, if you look through like the binaries on your like Windows computer as well, it's like it's hard coded in there. So if you like open an Engager or something, you should be able to find all this information pretty easily.
Okay, thank you.
Hey there, thank you for presenting this super interesting and I think an amazing way to learn exploitation. I hope you enjoyed the journey. Quick question, it looks like you used a bunch of tools, reverse engineering related and Windows RCP related. I'm curious specifically the step where you try to reach the vulnerable location, where you went through all the conditionals, can I reach them as a lower privileged user and so on. Did you use a tool for that, or was that through manual code review?
Are you talking about the one where I was trying to crash?
Yeah, like basically the slide with the control flow graph, where you then like said the purple arrows are the path that you're looking for, and how did you find that in the end?
Yeah, that was so. First, I wanted to find all the functions that would call that would like do some sort of interaction with the port struct, and then there was like a whole bunch of functions that did that. So I asked like Claude to help me like analyze some of them, and then I found like some potential candidates. And then the thing that made it easier was like putting all that, like chaining all of them with WinDebug, and then like stepping through them, and then like calling the function that interacts with the port struct, and then like seeing the fields that it changes like in WinDebug and stuff. And then I made like a helper script in WinDebug where it like printed out the entire struct with the field names and everything, so I could like see what values change in it like as I stepped through like instruction by instruction. So that was really helpful.
Very cool, thank you.
Yeah. Time for one more? Oh, one more question if anyone has anything. Oh.
So when you're registering, you're racing certain servers after the crash?
Oh, yeah, sorry, go ahead.
What's the difference? Because you're not racing it at startup. Is the timing similar when it tries to restart after the crash?
So some services are, like some RPC services are configured to do like automatic startup, and some are configured to do manual startup. So if when I crashed it, I didn't have to like race necessarily against it. I think that was more for like with the research that the Safe Breach was doing. All those RPC servers were automatically configured to start up like at runtime, but there was like some sort of delay. So then he was doing the racing. But with the crash, I found that for RasMan, I didn't have to like race to get it registered. It might it might be situation dependent. Like I don't remember if it was configured to automatically start up or manually start up, but maybe if it's like automatically start up, if it's configured to automatically start up, it like starts right after it crashes. I forget if RPC servers do that or not, so I'm not 100% sure, but thank you so much.